horizontal asymptote at y equals to 0. Okay, last one on here. EBM. Take the ratio of those leading terms. What does that simplify to?
3x.
Interesting. Which means end behavior is going to be like a positive sloping line, like similar to y equals to 3x, right? Like we could think about it as x approaches negative infinity, y would be approaching negative infinity. And as x approaches positive infinity, y is approaching positive infinity. Y is not approaching a finite number, which means h of x does not have a horizontal asymptote. No horizontal asymptote. Okay, and that's why it's not approaching a number. Which leads us into slant asymptotes, okay? Now, if we go back over here, if I graph the function that we were just looking at, okay, you can see if I graph y equals 3x, we can see how the end behavior is similar. As we zoom out, it's almost like they look like parallel lines, okay? So y equals to 3x gives us kind of this like blurry picture of what the end behavior is, okay? It helps us have some understanding. It's if we do a little bit of extra work that we can determine the equation that like gives us an even clearer picture of how the function's getting to where it's going as x gets infinitely large or infinitely small. Remember, the operation between the numerator and denominator is division, right? Like, it's polynomial division. Which means, remember when we did the polynomial division and you got q of x? So if we have our function, right, and we have n of x over d of x, that's equal to a quotient plus the remainder over the divisor. In the case, yeah, it's distracting. In the case that the degree of the numerator is exactly one more than the degree of the denominator, so obnoxious.
You sure it's a car?
It's like
the Tesla, bro.
It's the backing up.
Yeah, we gotta go slam out Elon, bro.
So patented.
I think it's like the car trying to stay cool.
It does sound like a Fortnite chest, though.
Fortnite chest when you're like under.
Yeah, it does. It does sound like that.
Oh,
He does. You know.
my dad plays Fortnite.
Okay, in the case that the degree of the numerator is exactly one more than the degree of the denominator, your end behavior model will be linear, right? We get y equals mx. If you were to do the division and rewrite n of x over d of x in this form, you would get this, right? mx plus b would end up being your quotient. in the case that the degree of the numerator is exactly 1 more than the degree of the denominator. So this is why we can say that the equation in the form of y equals mx plus b would give us the equation of the slant asymptote. As x is approaching positive or negative infinity, this will always end up approaching 0, and that's why the function ends up approaching mx plus whatever mx plus b is approaching. So positive infinity or negative infinity, but in the same way as mx plus b. Because if we're thinking as x is approaching positive or negative infinity, f of x ends up approaching whatever mx plus b is. Okay. This is the example we were just looking at. So we determined the end behavior model was y equals to 3x, and we saw that the end behaviors were really similar. If we go and do the long division, so doing what we were doing earlier, we have to do polynomial long division here, right? We think what times 2x squared would give us 6x cubed. That'll be 3x. And then we distribute. And we subtract. So minus 5x squared minus 12x. Bring the 3 down. We're like, what times 2x squared would give us negative 5x squared? That's going to be minus 5 halves. And then when we distribute, that'll be minus 5x squared minus 5 halves x, and then minus 10. And when we subtract, that ends up being minus 19 halves x plus 13. And that's our remainder. So like if we rewrite...
Is it plus 7? Oh, wait,
No, minus negative 10. So that means h of x, remember how with like quadratics, with equations of lines, we have all the different forms that are helpful. Like lines, we have slope-intercept form, point-slope form. Quadratics, we have factored form, vertex form that are all helpful. Like doing the division to rewrite this as quotient plus remainder over divisor is a helpful form for thinking about end behavior. So the function can be rewritten as 3x minus 5 halves plus negative 19 halves x plus 13 over 2x squared. I know it's yucky, I know. Okay. And then when we think about, but this is a kind of a helpful way of thinking about as x approaches positive or negative infinity, this will always go to 0. Right? Because the numerator's degree is less than the denominator's degree. And then that's why h of x is approaching positive and negative infinity in the same way as this line. So we can say that h of x has a slant asymptote at y equals to 3x minus 5 halves. So if I go back over to Desmos and look at this graph again, okay, I'll switch it back. Everyone look up here for a sec. So y equals 3x and then minus 5 halves. Notice how much closer that is to like merging with the graph of the rational function, like it just gives us an even clearer picture of what the end behavior looks like.
So does how does the remainder affect the graph? Or do we just ignore it?
The remainder doesn't. Like by thinking about the remainder, it's just rewriting h of x in this equivalent form. Kind of like if you were to take like a quadratic and factor it.
Okay.
It's the same thing. It's just this form that allows you to see end behavior,
Okay.
like why the end behavior is what it is.
If we didn't have a remainder, it wouldn't be a slant asymptote.
Then the graph would, well, it would. It's just the graph would be linear.
Okay.
Yeah.
Could you explain again how like we know that it's a slant asymptote?
Yeah. So we knew to look for a slant asymptote because of the end behavior model. So this is the same function that we were looking at on the previous page, where we saw that the EBM was 6x cubed over 2x squared, which ended up simplifying to be 3x. Now this isn't the equation of the slant asymptote, but it tells us that, hey, the end behavior is linear, like a line with a positive slope, not just a horizontal line.
So it can only be slant if its behavior is linear.
Yes.
Wait, what did he say?
Yeah,
He said,
what did he say?
what did he say?
Can only be a slant asymptote if the end behavior model is linear, like a positive or a negative sloping line.
So if there's no horizontal asymptote, then it
There wouldn't be a horizontal asymptote, and your end behavior model has to be linear. Remember how the example that I gave you guys before of when the degree of the numerator was more than the degree of the denominator? Your end behavior model was a quadratic.
like 3x squared, yeah.
So in that case, no slant asymptote, end behavior is like a quadratic. Like if I go back over here, and this is like kind of a big thing to be trying to present you guys with at the end of Friday afternoon, but that's okay. So if I get rid of these, notice if I change this to be a 5, where's my keyboard? Can I not be... Okay. So if I change that to be a 5, so that means that the end behavior model is y equals to 3x squared, right? Where'd it go? Oh no, cubed. I want it to be squared, so what do I need to do? I need to go, 4. I need to make that 4. There we go. For end behavior to be like y equals 3x squared. Do you guys see that? So this is the graph of the rational function. This is the end behavior model. So end behavior is like a quadratic, which is not linear. We would say that the end behavior like is not described by an asymptote in that case. But that's not something that you need to worry about in this class or in pre-calc honors. You will only be asked to identify horizontal and slant asymptotes. Okay, Xavier, you're getting your wish. Go find a spot at the board. Figure out the equation for the end behavior asymptote of this one. Then we're going to put it all together.
Okay. So
You guys go 3 and 3.
There's a
Linear.
So Seb, Xavier, so
Isn't it
Xavier,
linear?
Xavier,
There's
Xavier.
none.
Yeah.
Yeah, there's no.
so
Because it knew
No horizontal.
as
X
is
approaches
approaching
positive, positive, negative, negative.
Yeah, like this.
Okay, which ones do you like?
Like that.
I forgot.
Oh,
That one. As x equals infinity, 1
Is that what it means? Okay.
Actually, I should put my start.
Where do we go from here?
Now, you have to divide this by this.
long division.
Oh right.
Or
Or
Do you have to use-
Wait, we can do
Synthetic.
this.
Can be synthetic.
Oh, look. Do it.
We're going to say that.
So the remainder is 12 over 15.
Which means the slant asymptote is,
X minus 5.
so write out, where's the slant asymptote? Slant asymptote, SA.
1.
Hmm? S
No,
A.
like you just like abbreviate it.
Oh.
Slant myself.
S A equals X.
No,
What?
at.
The at symbol. You know, like
It should be an equation. Y
X
equals.
minus 5. No?
Yeah, yeah, yeah.
Yeah.
This is, you guys, when you put the remainder, you're just rewriting j of x in its equivalent form.
I see.
And that's where you can see,
X minus
as
one.
x approaches infinity, this is going to 0, and that's why j of x is approaching infinity in the same way as y equals to
Wait, so
x
what do I
minus
change?
5.
Oh. Said X squared.
Oh,
This?
yeah, yeah.
Because if you're plugging in really large numbers, think about what's happening to 12 over this.
There's not many
So like 12 over a million minus 2. 12 over a billion minus
This
2.
is
Right?
minus
Like
one.
it's
Why did
just
you
getting
say
smaller
minus
and
one?
smaller.
Yeah, wait, how did you get minus 5?
About plus.
what? Minus 5.
She gonna call me baby.
2.
Oh yeah, how did we get minus 5?
5.
Huh?
Oh, it's
Oh,
plus.
plus 5. Oops. My mistake.
It is minus 5. Get out, Max. Get a friend.
I'm sorry.
Okay, we're gonna put it all together now and graph rational functions. You guys already know how to find x-intercepts. We're gonna put end behavior, same with like how we did with polynomials, it's just these can be a little bit more complicated. We're gonna identify discontinuity, so if there's holes and vertical asymptotes, as well as end behavior, and then also the x-intercepts.
I told you to get out the way. It's so mean. Oh wow, that's a long.
Oh, shoot. What was that?
You know,
It's not that bad. Oh, well, it looks terrible with this all written over it.
I think our work was that bad.
Okay, so identify the domain and like any domain restrictions, figure out what the domain restrictions correspond to, right? So whether there's holes or if there's vertical asymptotes, right? That's what I mean. So domain, and then you're like, okay, these domain restrictions correspond to either holes or vertical asymptotes. Figure out end behavior. You can use end behavior model to help you do that. X-intercepts, you guys, for the x-intercepts, you can also use multiplicity to figure out like what's happening at each of the x-intercepts. I know, right? It's cool.
Yeah.
Totally. Y-intercept could be helpful. And then to figure out where the vertical asymptote is going, remember how we picked the values that were really close to the left and right, like 2.999, 3.001, to figure out whether it was going to positive or negative infinity. We're doing it all and we're mashing it together to figure out what these graphs look like. Uh-oh. Low power mode. Okay.
I haven't heard that audio.
Okay. So first of all, why don't we factor the denominator here? So we know m of x can be written as x over x minus 1 times x plus 1. So we can see that x can't be equal to plus or minus 1. Like the domain would be negative infinity to negative 1, union negative 1 to 1, union 1 to infinity.
Ball.
Where? Just start it.
no common factors, which means each of those domain restrictions corresponds to what? Good. So we have vertical non-removable discontinuities, which are vertical asymptotes. Do those in red. So we have non-removable discontinuities at x equals to -1 and x equals to 1. They're both vertical asymptotes. So I'm gonna graph those. I'm gonna put those in there. My iPad's really hot. Does not like doing all of this work. Okay. What was that? X and Y intercept are what, you guys?
What do I say?
You got it. 0, 0, right?
Yeah. Why do I say it like that? I don't know.
Now the only X and Y intercept is at 0, 0. Do you see how X is to the first power? So I actually know that the graph is going to cross through the x-intercept, like through the x-axis, like a line, just like it did with polynomials. Do I know which direction?
Yes. No.
No.
Don't we have to do that thing where you make it?
We have to do the test values, right?
Wait, how do we know 0, 0?
Because you're thinking what would make the numerator equal to 0? Right, wherever the numerator is equal to 0 will correspond to making the function equal to 0, right?
Oh.
And if we plug in 0, don't we get 0 for the y-intercept? I feel like I need to plug this in. Shit, charger over here.
Does your iPad use that one as the flash cord?
You don't think this guy's super.
I don't know. It uses this
You
one.
want
Yeah, shut up.
Ow.
Okay. Why is it not? I don't know if it's charging. Okay. So we can do test values to figure out what's going on as x approaches the vertical asymptotes. It might also be helpful for us to figure out end behavior before we do that. So why don't we think about end behavior model? To do that, we can look at the original and we're like, okay, this ratio will be our end behavior model. So the end behavior model will end up simplifying to be,
1 over x.
which means as x approaches positive or negative infinity, y ends up approaching,
0.
and that means for end behavior, we can say there is what? What describes the end behavior of this rational function? If y approaches 0 as x approaches positive or negative infinity for the end behavior model, that means that m of x also will, meaning that end behavior can be described by a horizontal asymptote at y equals to 0. So we can sketch that.
This is rough, folks.
Yo, we're gonna really make fun of my lines.
Okay. So here's the thing. We know there's only one x-intercept. If I do a test value, and I know that the graph is going to cross through, so we can be strategic here. If we think about choosing values directly, how about to the left of 1? So thinking about, here, I'll do this in green like I did earlier. So thinking about as x approaches 1 from the left, like what m of x is approaching, it's going to be either positive or negative infinity. But we can choose a value to the left of 1, like 0.99. And if we thought about plugging 0.99 into the function there, right? That would be 0.99 minus 1 times 0.99 plus 1. So that's going to be a positive over a negative, which means m of x would be approaching negative infinity as x approaches 1 from the left. So that means the graph is going to be trending down towards negative infinity as x approaches the vertical asymptote. It also means, because we know the graph crosses at the x-intercept based on the multiplicity of the 0, we know the graph is going to then have to trend towards positive infinity as x approaches negative 1 from the right.
What?
Because it's not bouncing off, it has to cross. And it can't cross again.
Wait, how do you know it has to cross? Like, how do you know?
Because the multiplicity, so the 0, the value that would make the numerator equal to 0 is 0. And it has a multiplicity of 1. If you set the numerator equal to 0, you got x equals to 0. It has a multiplicity of 1, meaning that the graph will cross at the x-intercept. And it won't be very flat. It'll be kind of linear. Mine almost looks too S-shaped. Yeah.
Wait, how did we, why did we get this blue lines
Oh,
from?
that's my graph.
No, I mean like, I followed when we were plugging in the numbers, but to the left of 1, shouldn't it, if we just said that it goes to negative infinity when it's to the left of 1, why is it going to positive?
No, to the left of positive 1. It's going down towards positive or to negative infinity.
So then it would be to
You're
the right
approaching.
of negative,
When you're approaching from the left, which is this side, you're going down.
but would the other one be to the right of negative 1?
Yes.
Okay.
Yes. And if you did test values, you'd get a positive value. And you could do more test values. So we want to figure out what's going on to the left of x equals to negative 1 and to the right of positive 1. So we still have a couple test values we need to do. So we can think as x approaches negative 1 from the left, what is m of x approaching? So picking a value, so like negative 1.001.
We put this into the original one, right?
Yeah. Well, the original or the factored form is fine. Either one. They're the same. You could do the simplified one though too. It's probably easiest actually to use the simplified. So we would have negative over a positive. So that means m of x is approaching negative infinity. We're putting all the puzzle pieces together. So approaches negative infinity. We also know that the graph can't cross the horizontal asymptote anywhere else. So the graph's going to just come up and trend towards 0 as x approaches negative infinity.
Can't we just plug in like a point?
You could.
Too?
Yeah, you could. And then thinking about what's going on to the right. So as x approaches 1 from the right, so doing like 1.001. That would be a positive over a positive, so positive infinity. Which means the graph will have to be approaching positive infinity to the right of that vertical asymptote and then come down and approach the horizontal asymptote. I have videos of all of these examples of me working them out and explaining them that I will also share with you guys in case I don't think there's any way we're going to get through all of them. But also I can tell you're all quite fried right now, as am I. But it's, again, just like with polynomials, like thinking about putting all the puzzle pieces together. So like if we compare, if we go over to Desmos and check out how we did. Look, we did good. That's like what ours looked like. Right?
It's better than when it's like super tall.
Yeah.
Half an obvious.
Okay. I think that me talking at you. So here's what I'm going to do. I'm going to put you guys into groups to try the next one at the board because I think that me just talking at you is not being helpful right now. And then I'm also going to share my explanations of each one of them. And then you'll also have the practice over the weekend. We can check in on Monday morning and answer questions about either the examples or problems from the practice before we do our Chapter 4 quiz.
Oh, it's very laggy.
Is it? No. Okay.
No.
Okay. Oh, let me stop recording.